Leetcode 371, sum of two integers, medium type problem, but of course this classification depends on your particular experience. Since here we are dealing with low-level concepts, bitwise operations, and so on, and if you are dealing with those on a daily basis, then probably it will be even easy for you. And on the other hand, if you are not dealing with them at all, and those concepts are not familiar to you, then it might be hard. Yeah, so that classification, maybe it's not inaccurate. I don't want to say that it's inaccurate, but it really depends on your particular case, especially for those kinds of problems which are not your traditional algorithmic style problems. And that's it. Yeah, so just don't get upset if you can solve it from the first try, since it's quite unusual. And let's just read the description. Given two integers a and b, return the sum of the two integers without using the operators plus and minus. Yeah, and of course we have a plus b, and normally we would do those are the inputs a and b, yeah, and we could just do a plus b. But the whole story here, or the whole idea behind this problem, is the thing which is happening normally behind the scenes when you do a plus b. Yeah, so we want to go as deep as possible, not as deep, as low as possible, and understand how the CPU performs the addition and replicate it here in Python using bitwise operations, so it won't be like as efficient as it could, since we still go through the Python layer. But it's not about efficiency in this case, it's just about learning how those things work under the hood. Yeah, so we will deal a lot with bitwise operations, and we will try to implement addition in such a way that we will not have to use those operators at all. And of course, the numbers can be also negative. So we will have to deal with this case where, let's say, we add -5 plus -10, and the output is also negative. Yep. So this is another complication or another difficulty, but everything can be done. And examples are very helpful. So 1 plus 2 equals 3, and 2 plus 3 equals 5. If you didn't know this already, yeah, you can learn it from those two examples. So now let's try to figure out how to solve it, and we will have to revise a lot of concepts. So first, let's start with bitwise operations, and to be precise, with bitwise operations XOR and or XOR comma and how they work. So let's do a quick example. Let's say I have following numbers 4 and 5, and I want to do 4 XOR 5. Then I need to first get the binary representation, which is 1, 0, 0, or let's use a 4-bit representation, and that is 4 in using those 4 bits. So this would be the number of 1s you take, the number of 2s, the number of 4s, and the number of 8s. So maximum we can store 15 here. And now for 5, we take 1 4 and also take 1 1, and then we can use that funny symbol for XOR, which is also used in Python. And what happens? We go, of course, bit by bit, starting from the right side or starting from the lowest bits. And 0 XOR or XOR 1 is 1, because XOR gives you 1 when both inputs are different. Yeah, so if you have 1 and 0 or 0 and 1, then you get 1. And then if you have identical inputs like 0 and 0, then you get 0. No, let me. So here you get 0 as well, and here as well. So the answer is 1. And that's how XOR works. And now the second example using AND. And AND gives you 1 when both bits are 1. In this case, only here. And the answer is 4. And so those are the 2 bitwise operations that we'll use a lot. And we will also use some other concepts, but let's not get ahead too much. Let's first do a very simple addition. Yeah, because already using just those 2 logic gates or bitwise operations, we can implement a simple addition. So how do numbers or how does binary addition work? And let's figure it out on a simple example where we have just 2 bits. So A, like this, B, and the sum. And what kind of options do we have? Of course, they can be either 0 or 1. And so the first option is 0 and 0. And then we have 0 and 1. Then we have 1 and 0, and then we have 1 and 1. Yes, those are all the options that we have. And the first 3 should be easy. 0 plus 0 is what? It's 0. 0 plus 1 is what? It's 1. Then 1 plus 0 is what? 1 as well. And here comes the fun part. So what is 1 plus 1? Well, it's 2, but we don't have this option in binary, so we have to put 0 here and introduce the third column called carry. And the carry for the first 3 rows is 0, since we can fit everything to the first bit or to the 1 bit for the answer. And the last one is 1, yeah? Since the sum will be 0, but we carry 1 to the left to the next bit. Yeah? So that's how it works. And where are those bitwise XOR and AND? Yeah, 0 and 0 gives 0. 0 and 1 gives 1. 1 and 1 gives 0. What is this? This is binary XOR or bitwise XOR. Then the carry is the result of AND. 0 and 0 is 0. 0 and 1 is 0. Only 1 and 1 is 1. So the sum is A XOR B. and carry is A and B, but carried to the left, meaning one more concept, shift to the left. And this shift to the left just moves the bit one position to the next digit on the left side. Yeah. That's it. And now we can do a simple example. So let's add 2 plus 3. And we can double check here. 2 plus 3 is 5. So now let's do this operation. And so 2x or 3. And let's convert it to the binary. So let's do this. Let's use this 4-digit format again. Alright, so 2x or 3 is 1. If I see it correct. And let's copy this again. And to end 3 is 1 here, here, and 0 here. So here is 1. Now carry is 2 and 3, which is and shifted to the left by 1, which is what? Here we got 2, shifted to the left by 1, which is 4. And if I shift it to the left, then this one goes here, and here I have 2 zeros, so we will get 4. And now is again the fun part. What happens next? You do this multiple times, depending on how big your numbers are, until b is 0. And each time you swap a and b with sum and carry. So the next sum will be 1 and 4, 1x or 4. This here. 1 is the following, and 4 is the following. Yeah, so here is 1, here is 0, and here is 1 as well, which is 5. And then we do the AND operation. Which gives us 1 and 0, 0, 0 and 0, 0, 0 and 1, 0 and 0 and 0, 0. So all zeros. This time is 1 and 4 shifted to the left is by 1 is 0 shifted to the left by 1, which is still 0. And we arrived at the final result. That's how it works, but there are more cases. which deal with the fact that sometimes the numbers can be very long. And then we will have to use a concept called masking, which will cut the numbers when they overflow, and we will limit them to 32 digits. So that's the next thing. And the last thing is dealing with those negative results. But we can already implement this part here. So while b doesn't equal 0, the sum will be a XOR, which is this b, and the carry will be a and b shifted to the left by 1. What we did just a second ago, and now we can return sum. And I think that sum is also a keyword in Python, so better add this underscore. Let's run it. And I forgot this swap. So a and b equals silent carry. And the first two cases work okay. And we exceeded the time limit for some cases and got just 8 out of 31 cases for it. Okay, so the next thing that we have to deal with are those overflows. So this is, by the way, CPU other in hardware works this way. And the next important thing is that hardware registers, so where the numbers are stored, are fixed size. And in Python, we don't have any limits on how big the number can grow, except, of course, for RAM. We can run out of RAM at some point, but theoretically it's unrestricted. And we want to limit it to 32 bits. 32 bits or 32 digits, the same thing. And for this, we will need so-called masks. So let's use this example with 4-digit numbers. Let's say I have a following mask, which in binary will be 111, 4 ones. And then I have a number, which in binary will be represented. My number X in binary will be represented like this. 1, 0, 0, 0, 1. So this is 1, this is 2, this is 4, 8, 16. 16 plus 1 is 17. So this is 17 in decimal. And one way I can use a mask is using, again, the bitwise AND. So if I do if I do the AND operation here, this, of course, you can always add 0 from the front. Then what do we get? We got only ones the way ones were before, but these ones whatever was outside of this range that the mask has defined, the mask only had 4 bits, and will be removed. So this one gets removed, and we end up with inside the mask, the range defined by the mask, everything stays the same, but outside everything gets removed, meaning turned to 0. So here we have those 3 zeros as it was, and only this 1 1, this first one stays the same. Yeah, and I will not attempt to write 32 bits here or 32-bit number, but the idea I think you can get from here. Yeah, so you can limit the size of the number to 32 bits or any other number of bits this way. So this is one way the masks can be used. And this is using the bitwise AND, and the other one is using bitwise XOR, which we'll talk about in a second, but let's create our mask. So the mask will be 2 to the power of 32. So two to the power of 32, which is 1 shifted to the left 32 times. Yeah, minus 1. And this will be this number with 32 ones in binary representation. And so each time we do an operation, we will also use our mask for restricting how big it can grow. And let's just quickly check if it helped already or we need the next step. Yeah, so it helped with 3 cases, and the next step are those negatives. So in the meantime, I prepared for you this example, which is the number with which we would end up having in the sum if we continue that algorithm that we described here and we already implemented. For example, for the following inputs, if we did 5 minus 8, which we know is minus 3, but if we run it through our algorithm, in the end, we would end up with having the following sum, which of course is not correct. But when you convert it to the binary, something interesting happens. We have all the ones and just here 0 and 1, which is almost something similar to 3. And to get, because of course the answer is minus 3, and to get to this answer, we first of all have to somehow distinguish those negative numbers from the positive. So how to distinguish? And once we know how to distinguish between negative and positive, then there is an additional operation on top of all of that we already have, just for the negative. Okay, so the way to distinguish is by taking the look at this leftmost bit. Yeah, it is used for having signed numbers. So how do you store minus in this kind of form? You have just ones and zeros. Well, you reserved some spot, and the spot which is reserved is already like it was already decided that this very leftmost bit will be used for that, but they could decide, or maybe there are some other formats which already decide on some other spot. But traditionally, or the way it is done in practice, it's just using this first bit. And if it's 1, then, and depending, of course, on how big your number is. So we decided that those numbers will be 32 bits, but of course, there could be other widths for numbers. But in case of 32 bits, this first one, the one to the leftmost one, will be taken to represent the sign, whether it's negative or positive. And if if there is a 1 here, we have a negative number. The number is negative. Yeah, so that's how it works. We reuse the number for another purpose. So we store everything, the whole information in the same number with 32 digits, and simply the one that's leftmost will be used for the information, whether it's negative or positive. And if 1 is here, then it's a negative. So this is the way we distinguish. We use the leftmost bit. And then if it's a negative, we have to do 1 or 2 more operations. One is bitwise negation, which pops up first time here. And the second is A, or the sum, which is the result, XOR, which we can use already in a Python notation for, and the mask. And that's it. So if we, now let's copy this. Add our mask here, but this time using not AND by XOR. What will happen? And the mask, of course, is all ones. We will have just zeros. And only here, because 1 and 1 XOR 1 is 0, only here and this place will get 1. So that's the first operation, this sum XOR mask. And then we do the bitwise negation, which in Python in particular gives the following result: x plus 1. So what is the result from this operation? The result from this operation is 2. So in our case, we'll have 2, and we use the formula 2 plus 1 is 3, and we end up with -3. That's it. So that's the way we handle negative numbers. Some additional work to be done, and now we have to first implement this check, and then this part. So the maximum number we can store is 1 shifted to the left 31 times, meaning 2 to the 31 power minus 1. And if the sum is greater than max, then what do? We do this, which is tilde or bitwise negation from some XOR mask. Otherwise, we just return this. Let's submit. And copy this outside. And we beat 100% of other competitors. Finally, all the test cases passed. And if you take a look at the final code, it's not really that complicated. Well, it's not really that big, maybe, or not that convoluted. But to understand everything what's happening here takes some time and practice.